All right, good afternoon, everybody. We're going to get this started. Todd Arnold, I'm hosting the student research competition here with Pingji. Our first speaker is Zinzi, is a third-year PhD student from the National University of Singapore. His research interests lie in the domain of programmable networks in exploring new applications, use cases, programmable data planes, software-defined networking in cellular and/or data-centric networks. So, turn over.
Oh, I have to use the microphone. All right. Good afternoon, everyone. So today I'll be talking about our ongoing work, which is towards accelerating the 5G centralized unit with programmable switches. So this is a joint work together with my collaborators, Archit, Satis, Nishan, Shahuan, and as well as my advisor, Manchin Chan. So before we get started, so let me give you some background in terms of the evolution of the radio access network in mobile networks. So we started off, in the legacy context, we started off with legacy RAN. So basically, the baseband unit is co-located, or basically is tightly integrated with the antenna or radio head. Gradually, we moved on to having centralized RAN, whereby we disaggregate the baseband unit away from the antenna. So we have a pool of baseband units. Subsequently, moving away from proprietary hardware, so we move on to commodity hardware. So now then we have virtualized RAN. But then eventually we are still limited by the fact that these baseband units still need to be in close proximity with the antennas. So subsequently, we have disaggregated RAN, whereby the baseband unit is further disaggregated, decomposed into a CU and DU, whereby the DU is a time-sensitive component which is located closer to the edge, and we can deploy the CU at the central office. All right. So then we move on to 5G networks. So in 5G networks, it is expected to support a variety of applications ranging from high bandwidth ones or ultra reliable low latency ones. So in this context, in a disaggregated 5G network, so you see that the CU is the aggregation point for the disaggregated RAN. So as the aggregation point, there's a potential that it could become the bottleneck. So it should not be, because in 5G we need to support ultra high throughput and also low latency. So to not be the bottleneck, so it must be scalable. But with existing commodity hardware or commodity servers, so it is a bit hard to achieve that. It's simply because CPUs cannot deliver bounded latency performance, especially it tends to have a long tail latency. At the same time, in order to support high throughput, it incurs high capex and opex. Especially, it will require a large number of servers in order to deliver the same amount of traffic. In order to deliver a high amount of traffic. So this is partly because of the slow CPU growth. So the problem becomes that how can we actually realize a scalable and performance CU? So as in this community, we are familiar with programmable switches. So obviously, programmable switches comes to the rescue. We all know that programmable switches are excellent devices for packet processing. So they deliver multi-terabits of line rate packet processing, like for the Tofino 2 up to 12.8 terabits per second. They give us deterministic latencies, and of course, they are cost effective. So for one programmable switch, there's a potential of replacing up to hundreds of servers. We have significant cost reduction and power reduction. But then it's not all good with programmable switches. For instance, there are some caveats. You have limited memory, and the programming model is really restricted. So then the next question to ask is that whether can we use the programmable switch to entirely replace the CU in the 5G RAN? So let us look one by one. So here, this is a diagram of the 5G RAN stack. So it sits between the DU, the distributed unit, and the 5G core for the CU. So between that, so it needs to do GTP tunneling. Okay, this is something that the switch can do easily. Fine. Then next, if you look deeper into the CU, you have the SDIP layer. So the SDIP layer, what does it handle? It does QoS flow mapping. Oh, okay, this is table lookup. Easy. Then further down, we look into the PTCP layer. So in the PTCP layer, so it needs to support a variety of functionality. For example, let me give you some example like packet sequencing, packet duplication or deduplication, ciphering, integrity verification, so on and so forth. But wait a minute. This is something, encryption or integrity verification, this is something that not a programmable switch can do well. Okay, this is something that, so we have something that the programmable switch cannot implement. So is this still a viable option for us? So as a matter of fact, we have options. So the key insight here is that not all functionalities in the PDCP are always necessary. Let me give you an example. So since most of our data traffic are encrypted, there's no need for another layer of encryption. And at the same time, even if there are use cases that require encryption that tend to be small. So for traffic that does not require an additional layer of encryption, we can just disable it. Okay, then we can just offload it to the programmable switch. So moving forward, how about use cases that require ultra reliable low latency? So there have been various discussions, and eventually there are even more options that will be disabled, like for example, packet reordering, and of course, including ciphering. So this will be disabled in order to really guarantee bounded latency. So from this, we can see that not all functionalities we really need it for most use cases. So to that end, so we came up with a prototype. Basically, we call it CUP4. So it takes a hierarchical approach whereby we have a CPU slow path, which supports all the functionalities of the CU, and a Tofino-2-based fast path that supports the key functionalities that we can support in order to offload most of the traffic. So in our prototype, so basically we implement our prototype on a Tofino-2 switch, and we integrate it with the open air interface 5G RAN stack. And this is deployed in our 5G testbed. So in our current prototype, we do not modify the source code per se, but instead we have an agent that transparently offloads traffic onto the Tofino switch for now. So if you look into the preliminary results, so in our evaluation, so you inject traffic using connected UEs, and we use another programmable switch to do timestamping in order to gather the measurements. So in terms of the latency, I guess this is not surprising. Oh, sorry. I guess this is not surprising. So we can see that the programmable switch can deliver very deterministic and very good latency performance. And at the median, it's up to 80 times better. So we can immediately see the benefits of a programmable switch in this context. So if we take a step back and look at the big picture of hardware acceleration in the 5G RAN, in the DU, so there have been a plethora of work that tries to accelerate the radio processing with GPUs and FPGAs. But at the CU, in terms of scaling it, there has not been attention to it. And today we are the first one to actually tackle it. And finally, in terms of our ongoing and future work, so eventually we want to fully integrate this with open air interface and add remaining support for the additional functionalities like packet reordering and header decompression. This is ongoing research. And we want to evaluate with more complex, larger topologies and the scalability potential in terms of number of users supported, definitely. And lastly, we also want to explore the integration of it with the UPF in order to truly support low latency use cases. So finally, thank you for your time. This is a summary of all the slides. Thank you.
Thank you, Zinzi. Your questions with 3 minutes.
Hi, I'm Sharad from Microsoft. Thank you very much. I really enjoyed your poster and this talk. So I have a couple of questions. So
Sure.
The first question is, this P4 switch is probably going to end up replacing the top of rack switch at the CU, right? It'd be too expensive to add another switch there. And that top of rack switch is already going to be performing a bunch of other layer 2, layer 3 tasks. So have you packed in all of those workloads onto the P4 switch alongside the additional workload that you're adding? And how does that have an impact on the overall performance?
Okay, that's a good question. So at the moment, so in our prototype, we only included basic layer 2, layer 3 functionalities. So in fact, we did not actually, we did not consider what are the additional functionalities that will be considered in the top of the rack switch yet. But even so, they are actually, I believe that there are ways to solve it in terms of in a switch, there are multiple pipelines. We can always join pipelines in order to have a longer pipeline to support this functionality. And I think it is still worth it in terms of given that the scalability, given the cost effectiveness of using a programmable switch. So yeah.
Cool, thanks. And then my second question is, just imagine for some reason we can't buy Intel Tofino 2 switches anymore. What will be the implications of your work for maybe using a DPU or SmartNIC instead? Would your work directly translate over? What are some interesting changes you would say?
I think yes and no. So I think in terms of scalability, a SmartNIC is basically in terms of the traffic that it can handle. I don't think it's that much of different than using a single server. So eventually you still need to have to buy N and you still need to buy N SmartNICs and N FPGAs. But as a switch, in terms of the capacity it can handle, it's much more than that. So I think there's a fundamental difference. And I think what the role of a SmartNIC can play is that it can basically offload the slow path here in this context. It can complement the programmable switch.
Eddie Kohler, Harvard. Thank you. So this is a potential bottleneck. Is it an actual bottleneck? Where are the actual bottlenecks in the system?
Right. I think at the moment, so I think there are no exact measurements to that, I have to be honest. But what we foresee is that eventually when massive MIMO comes, eventually we expect, so and plus millimeter wave, so we're expecting a lot more traffic that will be coming from the radio end. So ultimately, fundamentally, we want the CU to be as powerful as possible to be able to handle as many radio front ends as possible. This is because this it is able to deliver a much better user mobility experience and gives us more chances to do a radio optimization.
Thank you. Out of time. Our next speaker is.
Oh, all right. Thank you.
Thanks. All right, our next speaker is Mingran Yang. She's a fourth-year PhD student at MIT and is advised by Manya Gadobi. Her research interest is to build novel network hardware and enable data-intensive applications such as machine learning. She's a recipient of Microsoft Research PhD Fellowship and the MIT Presidential Fellowship. Floor is yours.
Thanks for the introduction. Good afternoon, everyone. I am Mingran Yang from MIT. Today, I am very excited to present our work, first demonstration of real-time photonic-electronic DNA acceleration on SmartNICs. Machine learning is taking the world by storm. As a prime example, ChatGPT is the fastest growing online application ever. In just 1 month in January 2023, ChatGPT served 100 million unique visitors worldwide. This is just one of the many examples of this machine learning renaissance. More applications are empowered by machine learning inference in cloud or edge data centers. As a result, billions of machine learning packets are flooding the data centers. And this has massive implications for rethinking our networks and systems. There are two requirements for serving real-time inference packets. First, latency, and second, energy consumption. Live inference query response time should be less than 100 milliseconds. In addition, for energy consumption, we should make applications like ChatGPT to be more energy efficient because its current monthly electricity consumption is more than 175,000 people. There are huge incentives to improve on these two metrics. So in this talk, I will present Lightning, the first SmartNIC system to serve real-time inference packets using photonic computing to achieve both low latency and energy efficiency. With the end of the Moore's law, photonic computing is revolutionizing the computing world. It can compute at 100 gigahertz, which is orders of magnitude faster than electronics. It also consumes only 40 attojoules per multiply accumulate operation, which is hundreds of times more energy efficient than electronics as well. However, photonic computing has never gained practical traction. Why is this? Before answering this question, I wanted to give some background on photonic computing. This is the type of computation that uses light waves to perform computation in the analog domain. Different from the electronic computing, photonic computing, here's an example of photonic vector multiplication. This is a commercial optical transceiver for optical communication. If you open up this transceiver, you will find a device that is laser, which is used to generate the light source. And there's another device called optical modulator, which translates the input electrical data into the intensity of the modulated light. To repurpose this device to perform matrix multiplication, we connect two optical modulators back to back and apply two separate electrical voltage data onto two separate modulators. The result of this double modulated light will be the effect of the multiplication of the two electrical data. And we can have a photodetector to detect the intensity of this double modulated light. And the result will be the result of matrix multiplication. I wanted to note that optical modulators and photodetectors are passive devices, and they perform the computation naturally as the light propagates through the system. However, this is challenging in a real-world deployment. The reason is photonic operations are mixed with the electronic ones in real-world machine learning inference. This is an example of a fully connected layer machine learning inference. As you can see, the photonic multiplication and those digital ReLU nonlinear functions are mixed together. As a result, a control logic is needed to coordinate the operations across electronics and photonics. And we need to support diverse machine learning inference packets. So we need a runtime reconfigurable system. How to achieve reconfigurable control from packets to photonics? To this end, our solution is to co-design photonics and digital systems. Our key innovation is a hardware programming abstraction to make control decisions on the data plane. By inserting this control decision in the data plane, we can make control decisions as data flies through the data plane. How should we design this abstraction? It should be simple to incur only minimal overhead. It should also be powerful to cover a wide range of DNN models. To this end, we propose Lightning's reconfigurable count action abstraction. The high-level idea here is to trigger an action whenever the count result reaches the target. Here, the count primitives keeps accumulating the specialized variable across digital data plus clock cycles. Once the result reaches the target, the count variable will be set back to 0, and we perform some action to trigger photonic computing. This is very similar to the concept in programmable switches match action table, but our count action logic can provide more flexibility and runtime reconfiguration. Putting this all together, we use this reconfigurable count action abstraction to connect the digital part and the photonic part. That is our Lightning SmartNIC. We design digital control around the photonic computing core, allowing Lightning SmartNIC to serve real-time inference requests. We spent about 2 years building the first fully functional Lightning SmartNIC hardware prototype. Our hardware prototype contains a 100 gigabits Ethernet interface and a Lightning data path implemented on FPGA with stacks and ADCs. In the photonic side, we have 4 modulators and 1 photodetector capable of running 2 MAC operations in parallel at 4 gigahertz. We also made a Lightning developer kit, which is made of fully off-the-shelf devices. Sign up if you are interested to get one. We further perform large-scale simulations, and our result shows that Lightning improves the average inference serve time by around 40 times, while reducing the energy consumption by around 54 times. To conclude, Lightning is the first photonic-electronic SmartNIC to serve real-time inference packets. Our count action abstraction enables runtime reconfiguration of photonic-electronic computation tasks without interrupting the data flow. We have open source hardware and software, and we look forward to working with members in the community to explore the exciting area of photonics. Thank you so much for your attention, and I'm happy to take questions.
Hi there, it's a great talk. So I had a question which is like, On the slide you had, which was showing the multiplication process, that makes sense the way that it works naturally, but doesn't that rely on a very fine control of the optical power that you're receiving? And like, I guess, more generally speaking, if you wanted to distribute your multiplication across multiple cores, is that something that you see being feasible in the future if you need to share intermediate results over a longer distance?
That's a good question. So in the testbed realization, it takes some effort to make the signal perfectly align with each other. But we are currently building a photonic chip. In a chip environment, it is more controlled, and it is naturally to support more cores on the chip. And that is our current effort to combine the digital part and the photonic part together, so that the control logic is more deployable in a real world setting.
Thank you.
Eddie Kohler, Harvard, thank you. So which part of this work would you say is most has been your contribution, your interest?
Yeah, thanks for the question. So the overall challenge of this work includes multiple dimensions, includes the photonic part, includes the system part, and also is the chip synthesis effort that we are currently doing. So my contribution lies mostly in the system design part, the digital logic around the photonic part, and also I've been actively working on the chip synthesis and building the lightning chip.
So, Alan Liu, it's really cool work. When you see this data plan has a series of analog, right, and then from the lights, when this data plan is too long, for example, for your more complex target, how you handle the noise, right? Like just curious, like, when do you have any limitation on that? Like how much you can handle and how much noise bringing could potentially break your accuracy?
That's a good question. So the noise in photonic domain, like there are thermal noise and there are a lot of noise that can caused by the environment. So in the testbed setting and also in our chip design in the future, we show in our paper that machine learning is actually very resistant to those noise. And we have emulation result taking all the photonic part in consideration. And we show that the image classification accuracy does not drop significantly due to the noise. It's just basically keep the same as the digital computation. And also in machine learning area, there are a lot of researchers have been working on taking the noise into consideration during the training process. So we can also include that in our system and consider that as the part to take those photonic noises as well in the training process.
Thank you. Let's thank our speaker.
Thank you.
All right, next up is Alon. Alon's a third-year PhD student and NDSG fellow at the Wireless Mobile Networking Lab here at Columbia. He received his bachelor's and master's in electrical engineering in 2020 and 2021, respectively, from Cooper Union, and his interests are in full-duplex wireless, physical layer algorithms, compressed sensing, and cognitive radio.
Thank you. How's it going, everyone? My name is Alon Levin. And today I'll be presenting experimentation with wideband, real-time adaptive, full-duplex radios. Now, this work is done as part of the FlexCon project here at Columbia, which stands for Full-Duplex Wireless from Integrated Circuits to Networks. And this is an interdisciplinary project that consists of 3 research groups at Columbia, encompassing experts in networking and communications, analog circuit design, and digital circuit design. All of these are important components of this. So here's a refresher on full-duplex communication. Full-duplex is the simultaneous transmission and reception on the same frequency, as compared to any standard wireless device, which only operates in half-duplex mode. What this gives you is increased system throughput and reduced latency, plus more flexible use of the wireless spectrum. The issue with this is that it suffers from very high self-interference, which is caused by leakage of your own transmitted signal back into your receiver. How bad is this? You've got some numbers on the screen, but to really drive the point home, if the received signal you're looking for is the size of a quarter, your self-interference is going to be the size of 100 football fields. American, not European. So this is the challenge that we're dealing with here. So what do we do about it? Well, we take a cue from the way your Bluetooth headphones work. You isolate the noise as much as possible, and then you perform active cancellation in the form of analog circuitry and digital algorithms. We do the same exact thing here. Now, what does this have to do with networking? Well, if you enable full duplex communication on the physical layer, you have ramifications for every single layer above, right? You now need to consider your scheduling, you need to consider your channel allocation. There are a lot of games that to be played here. However, it all rests on the necessity of working full duplex wireless boxes. So here at Full Duplex, we've developed 3 generations of these small form factor IC-based cancelers. Now, generally, you find self-interference cancelers to be delay line based, which makes them very bulky. We've worked on switch capacitor technology to bring down that size to the 2 millimeter by 4 millimeter size, right? And in the third cancer that we're demonstrating here today, this cancer is the most advanced cancer we've worked with to date, featuring a 16-tap full duplex radio, which can perform cancellation across a 50 megahertz bandwidth. This is great. It gives us a lot of room to play with, a lot of flexibility, but that comes at the cost of complexity. And if you want to have a real-time working system, you have to know how to address that. So the 2 goals we're establishing today in this project are to design a real-time adaptive controller that enables a highly complex programmable RFIC, such as this one, to achieve and sustain sufficient self-interference cancellation, and to integrate this IC along with this real-time controller into a complete full duplex radio that can transmit data over an actual link. So here's what we propose. Here's the node architecture that we presented at the demo at this conference. It consists of 5 primary components: the antenna interface, which provides that isolation, the RFIC, which I just showed you, the software-defined radio and associated new radio flow graph, and an intelligent FPGA platform, which performs the computations that you need. The canceller. Well, I told you it's complex, but how complex is it? I told you it's got 16 RF taps. Every single tap has its own configurable gain and configurable delay. If you start playing with all the knobs and levers, that gives you over 10 to the 19th possible parameter combinations. And for every single packet that comes in, you got to find the best configuration that will optimize your self-interference. And that's no easy task. So we've done this before at ISSCC in 2021, but this was on a tabletop setup. You had dedicated lab equipment, you had MATLAB. There was no communication, it was slow. How do we put this into radio? How do we build system intelligence to this? We developed an algorithm that runs in real time online that uses previous knowledge of the cancer's performance. For every packet that comes into the system, and I'm going to get to the communications in a second, for every single packet that comes into the system, we measure the self-interference that we're hearing. Initially, we do a one-time selection of taps and delays combinations. We select the primary settings we want to use, and then we compute the gains that we want to have on those taps in the filter. The FPGA configures the canceller, lets us know how we're doing. We measure self-interference again, and we iteratively adjust bit by bit until we get to the best cancellation we can get from this RF SIC. The communication is all handled by the software-defined radio and the associated flow graph that we built with it. We developed a packet structure that is based on the 802.11 AC data packet format. We designed pilot symbols in order to maximize our self-interference channel measurements. And we developed a controller that makes sure that the whole system is in loop, taking care of the FPGA communications, taking care of the cancer configuration, this transmit and the receive streams. Now, at the demo, we showed you a 2 radio setup, 2 full duplex radios, and a working link between them. But for the purposes of this presentation, we're going to go through the operation of one of them. Well, that video is supposed to work. But the idea is as follows. You have your transmitted signal. This is the outgoing signal. It's going into the circulator and out to the world. After that, you have your self-interference leakage coming through the circulator back into the RF SIC. And what you're seeing here, the results in red, which normally would be bouncing up and down, real-time optimization, is the result of cancellation after the circulator and the RFIC together. That provides you about 50 dB of cancellation, and the magic number to hit the noise floor to really enable the full duplex communication is 70 dB. Finally, the signal comes back into the USRP and to the radio, and we use a digital self-deference cancellation algorithm to bring it down to the noise floor, thereby enabling us to hear the other radio's transmitted packet. In terms of performance, we have convergence to the optimal RF SIC state within 2 optimization stages. The circulator gives us initially 26 dB of cancellation. After convergence, the RF SIC gives us another 24, and then digital SIC brings it down another 17 dB to reach that noise floor number of -77 dBm. And again, this all occurs in real time. I'm sorry the video couldn't play. We can show it to you afterwards, but this all happens in real time. With every single packet that comes in, you get an improved RFSIC configuration. So the question is, to conclude, what did we do here? Well, we set out with 2 goals in mind, and we achieved them both. We designed a real-time adaptive controller that enables a highly complex programmable canceller IC with over 10 to the 19th possible configurable states to achieve and sustain sufficient SIC for full duplex communications. That's 50 dB of cancellation across a 50 megahertz bandwidth. And on top of that, we integrated the canceller IC along with its real-time controller into a complete full duplex radio that can transmit data over an actual link, as we demonstrated yesterday. What goes next? Well, we're going to integrate this radio into the Cosmos testbed, as we have done with previous iterations of FlexCon radios, so that anybody all around the world can log in remotely and start developing on MAC layer and higher layer algorithms, routing, channel allocation, and the like. And as well, it provides the ability for anybody to explore additional applications, joint sensing and communication, physical layer security, and other very interesting games. Thank you for listening. I'll be happy to answer any questions you may have.
Hi, I'm Sharad from Microsoft. Thank you very much. I enjoyed your demo and your talk.
Thank you. My pleasure.
So I'm guessing the environment over here when you did your demo is very different than in the lab.
Yes.
Maybe you've also looked at or tried it out in a variety of other environments. Can you tell us how the performance of your SIC has been doing, either here in the demo or elsewhere, and and why?
Right. So that's a fantastic question. Here we actually, when we were setting up, we were having some issues with our antennas. So we actually demonstrated a wired link, but showing the same exact principles that you would see with an antenna. So there are still optimization games to be asked. How often should you reset your initial selection of taps and gains? That's an area of research. I believe Dinesh Baradia in 2013 gave a figure for how often a proper reconfiguration needs to be done. But that is something that we're looking into. We've mainly been working in a pretty stable environment so far.
Cool, thanks.
Nice presentations, and also sounds like it's a very big team effort. What's your specific contribution in this project?
So I jumped on this project 2 years ago. I spent the first semester, the first half year, developing the optimization algorithms, which are based on a sparse reconstruction technique. And then the remaining year and a half, I specifically have been working on this system integration across the whole, this radio-wide system integration. So when I joined the project, we had that laptop setting where we only had dedicated lab equipment connected to this IC. There's no communication whatsoever, and a VNA, it only sends sinusoids. You can't communicate in the modern day with that. So I brought it to where it is today, using these packet structures, using the radio, and enabling this communication with this IC. I don't want to claim credit for previous iterations of FlexCon work.
Cool. Very quickly, what's the power consumption of the radio right now?
I don't have that number for you. That is not something I've looked into yet, but when the full paper comes out, it will be included.
Thank you.
Right. Thank you very much.
Thank you.
All right, our next speaker is Yanxiang Wang. He's a third-year PhD student at the University of New South Wales, and his research interests are in light-based communication and sensing.
Okay, hello everyone. My name is Yanxiang Wang, and I'm coming from University of New South Wales, which is Sydney, Australia. Today it's my honor to stand here to show you my interesting work I'm doing recently. It's called EV-DMD. It's kind of a high-speed VLC system. So the VLC system actually means using the visible light to do the communication. So it can be divided in two classes. One is modulating the light source, and the other one is modulating the light propagation path. So for modulating the light source, actually it has some good advantages. For example, it has a high-speed data rate. The reason is that because we are controlling the light bulbs, we can control its color, its amplitudes. Most importantly, we can switch the light bulbs very quickly, like 20 megahertz. And also it has some, drawbacks, because if we want to control the light bulbs, we need to install external drivers. Also switch control the light bulb will cost higher energy consumption. So can we do something about these drawbacks? Yes. So the other way is just modulating the light propagation path. So in this way, we didn't control the light bulb, so it has a lower power consumption, and there's no requirements for the light source. We can use any kind of light, like artificial light, ambient light, sunlight, or infrared light. But it's not a perfect one. It do have the drawbacks too, because it has the data rate or data speed is low. So for example, 1 kilobit per second for the LCD shutter-based works. The reason is that it has a physical limitation for the LCD shutter. The transition time between two states on and off, is 4 milliseconds. So the maximum flipping frequency for LCD shutter is 250 hertz. So also there's another device called digital mirror device. Actually, there are millions of micro mirror inside. So the diameter is around 10 micrometers. What is important is that it has a very high flipping frequency. It can be 4.2 kilohertz. There's work which is published in the last year's NCDI, and it used the DMD as transmitter and used photodiode as the receiver. And it increased the flipping frequency and achieves 80K bits per second. But one thing we should notice in this work is that we do have lots of micro mirrors, right? But all the mirrors are the same state, all on or off. So it looks like a big mirror. So based on the current result, can we improve the data rate more? Is there a way to do that? Yes. The answer is yes. So like I said, one mirror is just one channel. If we can increase the channel number, for example, we just control the mirrors, individually. So every mirror can be regarded as one transmitter. So we will have lots of channels, and the total bit rate will be just the number of channels multiple the bit rate per channel. So if we increase the number of channels, we will increase the data rate linearly. So we have the transmitter, right? And this time we also need a new receiver, not a photodiode. Maybe we can use the RGB camera. No, we cannot, because there is a frame rate for the RGB cameras. They are exposed at a fixed frequency. For example, they are 30 hertz, 60 hertz, even with 120 hertz. But it's far away with the 4.2 kilohertz. Now we have a new option. It's called the event camera. So the event camera is a new kind of bio-inspired camera. Every pixel in it works independently. So the pixel just monitor the light intensity. When the intensity overpasses a threshold, it will tell you give you an event which contains the timestamps, the location, and the change direction. Means the intensity goes up or down. And the time difference between two events can be 1 microsecond, which means its sampling rate can be 1 megahertz. this will, just a good match with the DMD. Yeah, this is our setup. We have the transmitter as the DMD and the receiver as an event camera. Now we do the modulation. So from my speaking, it's both the transmitter and the receiver, they are sensitive to the on and off transitions. So we use the simplest one. It's on and off key modulation. And this top row is like intensity ground truth. And the bottom one is how the event generated corresponding to the intensity values. But different to the standard OOK modulation, actually we are watching on the up and down edges, because only when the intensity goes from 1 to 0 or 0 to 1, this time it will produce the events. So we are actually do the demodulation from the edges. So in my laboratory environment, we can increase the number of channels up to 1,800. So the total bit rate can be around 1.1 megabits per second. So it's a magnitude improvement. So for the future works, we can just push more number of channels, because the mirrors is billions. Also, we can develop new normal modulation algorithm for the event camera, because the standard CV algorithm cannot be applied. And also we can just propose a better modulation approach, not just simple OOK. Also make it robust to various working environments. So in conclusion, that we have achieved a high-speed VLC system, and for the working scenarios, we can just like in classroom, right? The teacher wants to share some secret file to students, and he can just project the live signals on the wall, and the students can get it from the camera, and no one can get it outside the room. That's the advantage for the VLC. Yeah, that's all. Thank you. I'm okay for all the questions.
So instead of the event cameras, have you considered an array of photodiodes? So in this way, you can also create multiple channels, but also keep the cost low. I know event cameras can be expensive, right?
Yeah. But here we cannot use a photodiode, because we are projecting like an image. If you are photodiode, it's just one value, one pixel camera. It cannot differentiate so many spatial locations. And for the price for the event camera, actually there are some new industrial products which is developed by Sony. In the future, it can actually be embedded in the camera, phone or the cars. So this will be solved in future, I think, the price thing.
What else? Are these VLC systems actually deployed today, or can you give a sense of what the deployment is in the real world for these VLC approaches?
Actually, you mean the application scenario, or
is it actually practically used today in the
yeah, actually the IEEE community just released the new standard for the light communication system. It's a BB standard. So I think it's a way to just solve the spectrum crunch, because all the other range is occupied by the RF signals. So also, especially for some scenarios that RF signals is not allowed to be deployed, like the military office or something like that. So the VLC system will be a better choice to deploy.
Okay, thank you.
Yeah.
All right. Thank you very much.
Thank you.
Right, our next speaker is Sushovan. He's a final year PhD student in the Department of Computer Science at Rice University. He's advised by Eugene Ong. He received his master's from the India Institute of Technology in Kharagpur. And his research focuses on energy efficient and high performance optical network architecture designed for future generation cloud infrastructures. This includes theory, algorithms, and systems. And he is currently on the job market looking for both academic or industry positions.
Thank you. Thank you so much. So, hi everyone. I am Sushovan, working with Professor Eugene Eng, and this is a joint work with Professor Arley Silva. So, we are from Rice. So, here I am going to talk about how to make all-optical circuit switch code for the future clouds to kind of achieve close to ideal performance. So I would start with the very status quo data center networks, which are the basic infrastructure behind the cloud. So as you know that it is consisting of multiple layers of packet switches, like top of rack, aggregate, and core. And here for the terms, I would just mention that I kind of consider the higher part of the top of rack switch as the core and the lower part of the top of rack switch as the edge. Okay. So now, as we know, the emerging applications are diverse, like high performance computing, machine learning, deep neural networks, and so on. And they have really stringent performance needs, right? High throughput, low delay, and so on. And on top of that, the advent of the domain-specific accelerators like GPU, TPU, etc., that makes this compute part really, really fast. So this makes us to a kind of scenario where network is really the source of the problem, and the network has to kind of cope up with such increasing speed. And here is our challenge, because we are at the end of the post-Moore's law era, where the electrical packet switches is kind of really hard to sustain because of the increasing gap between the capacity versus the power, especially that. So for example, if you kind of see that we have kind of studied some of the fastest switch which is available at the market right now, it has almost 2.5 kilowatt of power, which is a lot. So you can actually think of if you kind of need to make it non-blocking network at big scale with such kind of switches. So the power consumption from the cloud will be really high, and that can easily go beyond the energy budget of the industry. And we have seen similar kind of arguments from a lot of new industry papers like Google, Microsoft, and secondly, they would have a really high carbon footprint, which is really bad for the environment. So here is another way to think of this problem, which people have been trying to explore in the last few years, that all optical circuit switch cores can be one of the really promising alternative here, because optical switches can really save your power, but at the same time, it can preserve your performance. So I would just give you a very basic background of optical circuit switch, which is the building block of this direction. So optical switches are layer 1 switch, and it can actually configure your circuit at runtime like this, which is great. And it would have some amount of reconfiguration downtime, and that would vary from millisecond to hundreds of nanoseconds based on your actual optical switch hardware. But the good thing is, the trend is that we are going towards this faster and faster optical switch. For example, the Sirius paper from Microsoft, they have used the last kind of AWGR switches, which can kind of really tune very fast. So here are the very basic or fundamental advantages of these kind of optical switches. First, because they deal with light, they simply forward the light from one port to another port. They don't process packets, or they don't have queuing. So they are agnostic to data rate. They have really low latency. And the most important thing is they have really less power consumption. In most of the cases, it's zero. Okay, so with this background, let's try to understand that what are the proposals we have nowadays. So one of the few popular ideas for kind of all optical circuit switch cores are Sirius, RotorNet, etc. Now, I would like to mention here that they have very similar abstraction underneath. They might use diverse optical switches, but their underlying abstraction is this, that the the optical switches are going through a predefined set of circuit mappings. For example, here I focus on like Sirius, where you have these AWGS switches. So here the idea is if you change your the incident color of the light, that will make a certain port-to-port mapping, which is your like circuit. So if you have a sequence of colors across the time, this will actually convert a sequence of circuits. And underneath, you will get something like this, where every single TOR is going to get like connected with some other TORs exactly once in a whole cycle. And that thing is perpetually going on, right? To get a reconfigured non-blocking connection. So this kind of architectures are great because you don't need any kind of external control. This can go on like forever. So, and also this, you see that there is a sense of uniform distribution of bandwidth across the top of rack switches. So if your traffic pattern is uniform or close to that, it's great, right? However, the kind of the realistic data center network workloads have several characteristics, like they have high skewness and high interact volume. So by the term skewness, I mean that the interact traffic are like highly skewed. It's like it says that a few rack pairs have a lot of data to exchange, but a lot of rack pairs are like silent. And because your code is going to give an uniform distribution of your bandwidth, it cannot really enable you to use those underutilized path in general. So here is some of our simulation study, which shows that we have kind of varied the skewness of one of the popular data center traffic like cache, and we see that the kind of slowdown can be 7 times. And on top of that, if your bandwidth at the core is less, then this slowdown can be in kind of order of magnitude worse. So here is our idea, which is a new paradigm of architecture we are trying to like propose to use this all optical course in practice. So by now, like what we learned, that this kind of all optical cores are great for the uniform traffic. So let's make this core handle uniform traffic. So what we are saying that let's add another optical layer at the edge between the server and the top of rack switches, just like one layer of switches. And if we can reshape the traffic from the edge by tuning these optical switches so that we can have 2 goals. The first thing is that we can try to localize as much traffic as we can under the rack so that it does not reach the core first. And second, whatever traffic is going at the core, can we rearrange that intelligently so that it would be as close as like uniform, because that core is already made for that, right? So the kind of idea here is that we don't need to have an end-to-end control at the core. Rather, we can make small tuning like at the edge, like in a very like small scale, and that small tuning throughout as kind of accumulated way can help us a lot. So here is the idea that as I said, that these 2 goals, these 2 objectives is hard to kind of achieve at the same time, because they are not really so independent. They are like intertwined. For example, you see that this is a kind of simple architecture where you have 3 TORs and 2 servers like per TOR, and this is my server to TOR mapping right now. And this is my traffic matrix. So just below, I just show that, okay, what are the TOR server mapping and how much traffic is inter-rack and like intra-rack. So here you see that the localized traffic is 0, which is very bad. And also the traffic skewness is high. So we have used the Jane's fairness index to kind of measure the rack to rack traffic fairness. So more fairness means less skewness. Now, if you go for naively localizing the traffic a lot, then you can come up with a scenario like this. So see here we have localized almost all the flows, but you still have a certain set of flows which you kind of could not localize, and that are kind of concentrated on a certain rack pair. So you have improved the you have improved the locality, but your JFI is like still bad, right? So rather, what we are saying, we need something like this, where you should know that how much you should localize and when you should stop and spread the traffic accordingly so that you get the maximum benefit from both the worlds. So you see here we have, for example, localize the flow F1, which is a very big flow. So if you could actually localize, that would help a lot. But then there are smaller flows where you might not need to localize them aggressively. Rather, you can spread them intelligently to have symmetry. So you see here you have sacrificed a little bit of locality, but you got a very high JFI. So the goal is to jointly optimize both and to understand or obtain the right balance based on your scenarios. So here is the idea. I would take a few more minutes, is that we have come up with a non-linear cost function which can achieve these things at the same time. So it would not only give you penalty if your indirect traffic volume is high, but at the same time, it would also penalize you if your indirect traffic variance is high. So I would kind of quickly show you some of the outcomes, is that based on our simulation, and we have done experiments also, and we see that we can get very close to a non-blocking networking performance, and it can actually balance based on your scenarios. And we have very nice, I don't know what the thing is, but somehow the PowerPoint got having a problem. Sorry for that. But we have a better trade-off also. Thank you.
Thank you. All right, we have time for a question. One.
Hi, I'm Sharad from Microsoft. Very interesting and unique idea. So I'm wondering, how does your proposal compare to topologies where a server may be connected to multiple top-up rack switches?
I see. So are you saying that the multi homing kind of architectures, is it multiple NICs from the server?
Yeah.
I see. So that is a good point. I mean, we did not evaluate that so far, but what I feel that maybe you might get a kind of equivalent or similar performance with that. But point is that here we are kind of also focusing on the performance cost trade-off or the performance power trade-off. So we need a very minimal amount of hardware or transceivers here. Under that, I think we can give a very good trade-off across the whole space compared to the other architectures.
Okay, but also consider failure modes and the advantages that you get.
I see. Yeah, sure. I mean, the power is one of the major argument here. Thank you.
Hi, this is Shiva from MSR.
Hi.
Can you shed some light on the prior work that looked at the same problem, if there are any, and how did they handle this?
Sorry, can you ask me the question?
Are there any prior works that looked at the same problem, and what are their approaches, and do they differ?
I see. So I think, yeah. So one line of prior work was to kind of to give some kind of extra optical switches, but to kind of had a few links from each, of the torch switch, and that part of the optical core can be more dynamic. It's not the round robin core, but that can work as a parallel. So if you have certain flows with bigger flow size or higher deadline, so they kind of bypass those things. But they are all the rack level solutions. You still need to go through the rack, but here we are trying to solve the problem from the edge here, right? Mm-hmm.
Thank you.
Thank you so much. Sorry for the last slide. I don't know how it happened. Sorry.
All right, this is our last presentation. It's going to be a little shorter. I'll introduce Eric here in a second, but he is an undergrad, and he was the only presentation poster selected in the undergrad category to move forward. So that's why it's going to be a little bit shorter. We wanted to give him an opportunity to present his work as well. All right, so this is Eric. He's currently an undergraduate at Georgia Tech, and he's working with Ahmad Saeed. He's currently investigating how resources and congestion are handled at the microsecond scale, and he's open to applying to graduate schools next year, as well as opportunities for this upcoming summer for internships.
All right. So, one second. All right, cool. Thank you. So, like you said, I'm Eric. I'm from Georgia Tech, and I'm presenting this poster on understanding interactions between overlay control and core allocation and low latency network stacks. And again, this is going to be really short, just a couple minutes. So if you have questions, let me know after. All right, so to do our setup, let's just imagine really quick a server that has a bunch of cores to process tasks. These tasks will come into queues, and in this scenario, let's just pretend that we have per core queues. From there, we might have a core allocator. So there are systems that have been proposed to dynamically allocate cores with the goal to be more efficient with our CPU utilization. In this case, we are adjusting a capacity to meet some observed load. On top of that, we have clients that will be sending tasks into these queues, and often this is unpredictable. So to manage those, we introduce an overload controller. This prevents too many requests from hitting the server at once. And in this case, we almost have the opposite to the core allocator. We have something that is adjusting load to meet some observed capacity. From there, we see that we have some potential for interference with these two control loops. What happens when these interfere with each other, and what problems arise in those circumstances? In this case, we are analyzing Shenango as our core allocator and Breakwater as our overload controller, and we're using simulations to investigate these systems. Some scenarios that we investigate are sudden shifts in load, along with tasks that are on the microsecond scale with distributions both exponential and bimodal. We are varying the RTT and also the specific configurations of both these systems in order to see what happens as they interfere, especially with similar target delays. So one problematic scenario that we discovered is, let's imagine a sudden shift in load that introduces a burst of requests to the system. So as this burst hits the server, we see that high queue delays start forming as they get backed up in the queues, and the overload controller starts to do its job. It starts to emit less load and even drop some of the packets as needed to deal with the overload. On the other side, the core allocator starts to add cores, as it should, but this takes some time. So while this is happening, we experience less load in the system because the overload controller has already pulled back on load and dropped packets. So some of the cores can actually park even though we are experiencing overload. This is concerning behavior, but there are actually more problems on a larger timescale as well. Here we have the exact same scenario. That same shift in load is on that red dashed line again, and this is actually from the exact same simulation. And here we can see that the overload controller is trying to slowly probe up to meet that new load. Again, we are overloaded, so we should be using the max capacity of the server. But we can see that because it assumed that fixed capacity to begin with, and that dynamic core allocation is breaking that assumption, it is slow to adjust to the new offered load from the clients. The core allocator itself can be allocating cores on the microsecond scale. So it is capable of ramping up to the max possible throughput of the system very quickly. But here we see a ramp up of the overload controller more on the millisecond scale. So to fix this, we do have some patch solutions that are more detailed in the abstract paper, which involves coordinating the controllers. But we kind of understand that as a community, there are always going to be problems when we have two control loops that are interfering with each other. And we think this is worth exploring and that there is more room for general solutions in practice. That's all I have. Thank you.
Any questions? Excellent. All right.
Thank you.
Good job. All right. Thank you all very much. The winners of the graduate level one will be announced tomorrow at the end of SIGCOMM. And for the judges, just wrap up, put your notes and please submit. And thank you all very much for attending. Great job.